Hello, I'm Jason Martinez, and today I'm going to be talking to you about what's new with step-by-step physics and more. So, over the past few years, we have been greatly expanding our formula coverage as well as our coverage for step-by-step functionality. And I'm going to show some of that as well as some of the various improvements we've made over that time period. So let's start with the formulas. We've added hundreds of formulas over the last few years. Here we have a simple plot showing from alpha's launch to almost current day number of formulas that are contained within uh, Wolfram alpha. And these are the formulas that you see when you have little input fields and can get all the various results in different units and so forth. So obviously there was a big ramp up at the beginning. Um, we had a bit of a fallow period, but in the last several years, we've added around 700 new formulas. And that includes adding those formulas to formula data, which is the Wolfram language equivalent for, uh, for formulas. Uh, and here is just sort of a sample of those formulas that we now have in the language. This is weighted towards the size is weighted based on how many of those similar formulas can be found in the set of new formulas. So there's been a lot of mathematics formulas added, but also a lot of mechanics formulas, various engineering types of formulas, and so forth. Now, on the step-by-step side of things, we're also trying to increase our coverage of these new formulas, which is to say, how many of these formulas can we generate usable steps for? So this, our step-by-step coverage will go through and take your input values, plug them into the formula, perhaps give you some physical understanding behind the problem, and then work through the algebra and other calculations to get the final result. Now, to improve the coverage, we have to take into account two major complications: hidden factors and temperature arithmetic. So hidden factors are basically little hidden conversion factors that exist in formulas, particularly empirical formulas, um, that are usually omitted in the classic version of the formula to avoid cluttering up the expression. If I can just skip ahead here for a moment, the big example here is BMI. So BMI is just weight over height squared, but it has a hidden factor because we want the units to be in meters and kilograms. And so on Wolfram alpha, we obscure that factor. But when we go through the steps and actually plug in numbers into this formula, we need to actually acknowledge those factors and acknowledge that we are going to make these conversions. The same thing for pH, where we have a calculation looking at hydrogen ion concentration, and we take the logarithm of that. But you can't take the logarithm of quantity, so there is, in fact, a conversion factor that divides out the units, in this case, moles per liter. So one part of increasing our coverage was to acknowledge these factors and also to incorporate them into our calculations where we bring the various units into alignment and make sure that they're all easily compared to each other. So here for BMI, since we're working in feet and inches and pounds, we need to convert our conversion factor into comparable units. So feet squared per kilogram in this particular case. Coriolis effect is another example where we have to convert revolutions, because we're looking at the rotation rate, into radians. Side effect of this is we're then able to better access formulas that have behind the scenes some extra equations in their calculations. So, for example, the Richter scale has simple single equation case, very straightforward. Richter scale magnitude is dimensionless. There's no hidden factors or anything in there. But we also want to include the equivalent mass of TNT. This can't be just a simple unit conversion because TNT is where we're talking about mass of TNT, not energy of TNT. And so we have a hidden formula, a hidden equation in this formula that does that calculation. But we can exclude it from the step-by-step in this case. And the same thing with law of cosines, where we have some extra calculations for angles. So handling that was an extra bit of a challenge. The bigger challenge, however, was dealing with temperature. So temperature units are complex because they exist on a scale. So if you're adding or subtracting, multiplying or dividing, you need to decide what does it mean to be combining these units. Now, for formulas, most of this is looking at differences, thankfully. But even there, we have to be very careful. If we were just to deal with this particular calculation here, like you would feet in meters, we might say, oh, that should just be 283 Kelvin, but that's not correct because 0 degrees Celsius is equivalent to 273.15 Kelvin. And so the answer should be something different. And it shouldn't even be in kelvins, strictly speaking. It should be in Kelvin's difference, a unit of temperature difference. Now, temperature difference, we can do calculations in the same way we would do feet and meters and kilograms and so forth. But for temperatures themselves, we need to account for the 0 point because we're working on a scale. So the first part of this was just to make sure that our various temperature conversions were acting properly. So here we've looked for the fluid temperature from the Brinkman number, and we get an answer in Kelvin, but then we need to calculate that in terms of degrees Fahrenheit and degrees Celsius. We haven't yet covered degrees Romer or any other more esoteric temperature scales, but we hope to get to that fairly soon. And then for temperature difference units, we can look at boiling point elevation. That's to say the amount that the boiling point is elevated based on the materials dissolved within the solution. And that gives us a straightforward answer in Kelvin's difference. And then we can convert that into degrees Fahrenheit difference or degrees Celsius difference. Now, when we get to doing the calculations together, where we have 2 units in a temperature scale, and we are going to get a temperature difference in the midst of our calculations, we then need to make sure that everything's in the same scale. That way we don't have any confusion about 0 points or that sort of thing. So in general, when we're involving two or more temperatures, we convert them all into kelvins. And then we can proceed with the rest of the calculation. But there are some formulas that are not done in a Kelvin scale. Pasteur units and thermal degradation units all assume the calculations will occur in degrees Celsius. So those have an exception where we tell our step-by-step functionality, oh, these particular types of formulas are assuming Celsius, convert everything to Celsius. So we do that, and then we can put that into our formula, which, as you can see, has this factor that is entirely in degrees Celsius. All right. Getting back to the formulas themselves, We've also been adding some functionality to allow Wolfram Alpha to recognize when a result or an input is non-physical, where it's beyond the physical realizable limits. So this might be simple things like complex values, or a place where you have a negative value, but the physical quantity that we're discussing can't be negative, like a negative radius or a negative mass, or values that go outside of what is possible, which we'll look at an example in a moment. So in those cases, what we do is we sort of highlight that these are non-physical. So we gray out the result text. We tell you that these are non-physical. We tell you a little bit about why that's not reasonable, but we don't suppress those results, and we don't take away any step-by-step functionality. So you still get all the same results you would have otherwise gotten through Wolfram Alpha, but you also get this extra physical insight into the answer. And here we have a different example where we're looking at sound levels, and one of the inputs is 300 decibels, which is far beyond what the Earth's atmosphere can conduct. So for the purposes of this formula, that's outside the physical range. And so we let you know that. Now, there are a few exceptions to how we do this. And they fall into two categories. The first are just cases where we don't have a good alternative. We don't have an intuitive way at the moment to include vectors in our Wolfram Alpha input fields or results. So we allow negative values for velocity and acceleration and distance to indicate direction. So most of the formulas that are using these are one-dimensional. And so a negative value just means we're going in the opposite direction or accelerating in the opposite direction. Strictly speaking, these would be vectors in a physical sense, and their magnitudes would always be positive. But because of the current technical limitations, we have to allow that. The other case is where we felt that it was better to allow some non-physical values because they include some of the fun of working with Wolfram Alpha. So this includes things like superluminal velocities, which would otherwise complicate things like figuring out what warp factor 3 is in terms of the speed of light, or looking at atomic numbers for very massive particles. Now we've also applied this to input fields. So if you've put in something that's non-physical in that case, like a negative moment of inertia, then it will tell you that's an invalid value. And this is something that we've always had, but now it's just being applied more generally. And this will also impact some parsing. So in terms of steps, like I said, we still provide all the steps. So if we did our case where we get a negative radius, and you clicked on the step-by-step button, you would get this expression here, this set of steps here, and it would go through, show you how to do all the calculations, do the algebraic manipulation, put in the values, simplify the result, and then it would tell you that, hey, this doesn't make any physical sense. You look at the results and see that the radius is not a positive number. And we can do the same thing for the case I showed you with the sound level, where we put in all the results and we get back our final sound level, equivalent sound level, but it's outside the range of what's physically realizable. All right, so let's look at some other improvements for step-by-step. So one thing we've been doing is trying to add more steps for some of the simplification areas of the calculations. And so one thing that's been implemented in the last this last year and is just coming onto the website now is the ability to dig into the simplification of units. So here's a very simple example. We looking at average velocity, and we want to find the distance covered over a period of time. So we have a time, we have a speed, we put those in, and we get a distance. This is a straightforward one. Though I'll have a more complicated example in a moment. But basically, you can click on the little button here. There'll be a little orange border here, and then it'll give you a more detailed answer to what the result should be, how to go through the steps of simplifying that. Here we have Reynolds number. This one multiplies four different quantities and arrives at a dimensionless result. And we can click on that result, and then we can see how we convert all the units into something that's comparable, and simplify that down to the answer. And we have another example here where we're just doing the same thing, where we have joules and joule seconds, and we need to divide those out. And we're hoping to expand this so we can do more complicated cases where we're adding multiple quantities of different units, and then multiplying and dividing and so forth. The other area that we're working to expand our step-by-step functionality is just adding more physics, more explanation of how you get from the basic principles to the equation itself. So one way has been to just add new steps. So here we have one for throwing a projectile straight up. So we get a diagram that shows our initial height. We should get a maximum height, and it comes down to the ground over a period of time. And we want to find the maximum height. And so it'll go through and say, okay, well, we know that energy is conserved. So we have an initial and a final energy, or in this case, maximum height energy. We can break that up into kinetic and potential, go through the steps of adding all these, expanding these out. And then we know that at the maximum height, that it's not going to be moving up anymore. So we can simplify that out, bring terms over, and eventually arrive at our final equation, which we then can put in our numbers and solve for the actual result. We have done the same thing for releasing a projectile from a height. So where we throw it from a height, we do the same sort of calculation, which I'm not going to go through again, get the result. That also added the classical problem of a bouncing ball, where you drop a ball and it's going to bounce up a certain percentage with each bounce. And we want to find out things like what's the height after the third bounce, or how much distance is it going to cover up and down, which is this particular case here. So we start with the definition of the restitution coefficient, which is the square root of the height after the first bounce divided by the initial drop height. We do some manipulation of that to get our height after one bounce, and then we can repeat that to get the height after n bounces, and then we can use that to then work out, okay, well, we got to go up, we got to go down, then up, then down, then up, and so forth. And that's a finite sum. We do that calculation, and after simplifying those various terms, we can finally get the height covered from drop point to the height of the third bounce. Same thing with components, where we just include some diagrams to show you what's going on, what are the terms that we're interested in, and how we get the final result. Now, not every problem needs such a lengthy introduction. And so a lot of formulas we've added basically just a little bit of text that explains what the equation's about, what the terms mean, and a graphic, if possible, that sort of shows you what those various variables correspond to. So we already saw centripetal acceleration briefly. So here we have an object moving along, maybe on a disk, maybe just in a circle. It has a velocity. It's at a certain radius from the center. What's the acceleration holding it in? Or the classic problem of two trains, each leaving a station at a given time with different velocities and a distance from each other. When do they collide? And so it just gives you a sort of physical understanding of what you're looking at. This is particularly more interesting for more complicated cases. So here we have Boyle's law, which is thermodynamics type calculation or statistical physics, where we have a gas under pressure, and we keep the amount and the temperature static, and we vary volume. And how does that affect the pressure? Or Graham's law, where we have two gases, each of which are escaping from an identical container, but they have different masses. And we want to know what's the rate at which each gas is escaping relative to the other. But some cases it's just going to be text. So the probability of exceedance is a statistical formula where we basically sort of characterizes what's the likelihood for a given phenomenon that it will exceed some critical value. So this could be um, earthquakes or something of that sort, where all right, there have been these many earthquakes over this period of time, and so many of them have been magnitude 6. What's the likelihood in the next period of time increment that we'll see a earthquake with a magnitude 6 or higher? And so that just sort of works through the logic of that and tells you what the assumptions that we're making are and what our inputs are. And then lastly, we've been adding even more dedicated steps coverage. Uh, one very recent example has been adding steps for charged balls and charged spheres in terms of finding their electric fields and their electric potentials. These formulas on Wolfram alpha are piecewise formulas, which makes it difficult within the current structure to handle. So adding custom steps was the easiest way to sort of cover these unique cases. And it also allows us to go into more depth about how you get those formulas. So here we have a non-conducting sphere with a uniform charge spread over it, and we want to find the electric potential. So we say, okay, we know Gauss's law. We look over the closed surface. We know and figure out what the enclosed charge is. So we can just use simple geometry to find out, okay, what's the relative volumes from that and the total charge. We know how much charge is within the sphere. And then we can apply that to apply Gauss's law to integrate. We know that the electric field over the surface area is going to give us the result that we already know for the flux. So we can invert that, or we can sort of simplify that. So we know the electric field is constant because it's uniform. It's not going to change depending on which direction you're looking at. And we know that because of the spherical symmetry that is pointing out all radially. Do the integration, apply what we already know, And then we have the electric field. And then we can go and take that to find the potential. So then we repeat the whole process for the field outside and the field inside. And we can break out all those steps. But once we do that, we have all of those together. We put them, do the integrations, combine all the terms, and we get the final potential. And then we can do the calculation. Another example of new formulas is shadow length. So this is looking at, all right, we have some sort of reference. We have perhaps in this particular case, we have a light source. We know how high the light source is. We know what the height of the person is. How long is their shadow? I believe that's what we asked for here, yes. And so we can use similar triangles to combine these terms and find how they're similar, and then thereby solve for S. Or we could do that for the sun. In this case, we don't know how high the sun is, but we know what angle it's making. And more importantly, we have some sort of reference object which has its own shadow. So perhaps, we know that we're 6 feet tall and our shadow is 8 feet tall, and we know the building's shadow is 12 feet tall. Then what's the height of the building? And there's a few other of these where we look into differentials, because we're trying to look at, we have a moving object and we're seeing how much the shadow is growing or how fast the tip is moving, those sorts of calculations. All right, I'm just going to quickly bring us to a conclusion here. So back to the Wolfram language, we've upgraded formula data to handle around. That's our functionality for accounting for uncertainty in measurements. So if you use around in formula data, it will do all the right calculations, and you'll get back the around object with the proper amount of uncertainty in the results. You can also use intervals if that's something you want to use, and all of that will just work. And then lastly, we're always trying to expand as we expand our formula coverage, we also want to make sure it's easier to find formulas. So within the Wolfram language, you already have access to formula lookup, which not only looks up formulas based on their name, but you can also look up categories as well. And so find all the formulas that lie within kinematics or capacitor and so forth. And we are working on something for Wolfram Alpha. Hopefully you'll be seeing that in the next year, but I can't talk too much more about it. And if there are other functionalities or formulas that you'd like to see in Wolfram Alpha or the Wolfram language, please do let us know. Your feedback will be very important for us in determining what we're going to pursue next. Well, thank you for your time.